Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Have you ever wondered what holds everything together at the molecular level? Well, today we're delving into the fascinating world of bonding and crystal structures. These elemental relationships form the backbone of our physical world, from the structure of the diamond on your ring to the composition of the very air we breathe. We'll be starting at the very beginning, illuminating how atoms combine to form molecules through the magic of chemical bonding. Then, we'll take a closer look at how these molecules arrange themselves into crystal structures, creating the materials that make up our everyday life. We'll also dive into the crystal structures of common oxides, sulphides, and silicates, giving you a deeper understanding of the world around you. So, whether you're a chemistry student or just a curious mind, we've got a lot to explore together. Ready to explore the world at the molecular level? Let's get started. Chemical bonding is the glue that holds atoms and molecules together. Now, what does this mean? Well, let's dive into it. Imagine atoms as social butterflies. They love to interact, to mingle, and to form connections. The result of these atomic interactions? Chemical bonds. These bonds are the heart and soul of chemistry, the invisible links that hold atoms together to form the vast array of substances that make up our world. Now, there are three main types of chemical bonds we'll be discussing: ionic, covalent, and metallic bonds. Each of these bonds is unique, with distinct properties that influence the characteristics of the substances they form. Firstly, ionic bonds. Picture a strong, silent type giving a gift to a chatty, outgoing type. The strong, silent type is an atom that has an electron to spare, and the chatty, outgoing type is an atom that needs an electron. The result? An ionic bond, formed through the transfer of electrons from one atom to another. This gives rise to the formation of ions, charged particles that result in substances with high melting and boiling points, such as table salt. Next up, covalent bonds. Think of this as a shared secret between best friends. In this case, the secret is a pair of electrons shared between two atoms. This sharing results in substances with lower melting and boiling points. Think about water, H2O, where the oxygen and hydrogen atoms share electrons to form a covalent bond. Lastly, we have metallic bonds. Imagine a sea of electrons flowing freely among a lattice of positively charged metal ions. This free movement of electrons gives metals their characteristic properties such as malleability, ductility, and the ability to conduct electricity. So whether it's the salt on your fries, the water in your glass, or the gold in your jewelry, chemical bonds are at play, defining the properties of these substances. Remember, chemical bonding is the first step to understanding how substances are formed. So let's keep exploring, and soon you'll see the world in a whole new light, through the lens of chemistry. Now that we have a handle on bonding, let's move on to crystal structures. Crystal structures, in essence, are the orderly arrangements of atoms, ions, or molecules in a material. This organization plays a crucial role in determining many of a material's properties, such as hardness, conductivity, and even color. It's like the architectural blueprint of substances at the atomic level. To understand crystal structures, imagine a room filled with identical spheres. The way these spheres can be packed together represents how atoms arrange themselves in a crystal. Depending on the pattern of this arrangement, we classify crystal structures into different types. First off, we have the simple cubic structure. This is the most straightforward arrangement, where each atom is surrounded by 8 others, forming a cube. Picture a box of neatly stacked oranges, and you've got the idea. Next up is the body-centered cubic structure. This is a bit more complex. It's like the simple cubic structure, but with an additional atom in the center of each cube. Visualize a cube of 8 oranges with one more in the very middle, and you've got a body-centered cubic structure. Finally, we have the face-centered cubic structure. Here, apart from the corner atoms, there's an additional atom in the center of each face of the cube. Imagine a cube of oranges with extra ones on each face, and you've got a face-centered cubic structure. Understanding these structures helps us predict how a substance will behave in different conditions, and how it can be manipulated for specific uses. It's like knowing how a building is constructed helps us understand its strength, stability, and potential uses. So whether it's the diamond on your ring, the silicon in your computer chip, or the salt on your fries, every substance around you has a crystal structure that defines its properties and functionality. Crystal structures provide a blueprint of how substances are organized at the atomic level. Now let's apply what we've learned to some common substances: oxides, sulphides, and silicates. To start, let's consider oxides. Oxides are compounds that contain oxygen and another element. If you've ever seen rust, you've seen an oxide. Iron oxide, to be specific. The crystal structure of an oxide can vary greatly depending on the other element involved. For instance, in the case of iron oxide, it forms a complex cubic system which gives it its characteristic reddish-brown color. Next, let's move on to sulphides. Sulphides are similar to oxides, but instead of oxygen, they contain sulfur. A common example is iron sulfide, also known as fool's gold, due to its deceptive golden luster. Iron sulfide possesses a cubic crystal structure, with each iron atom surrounded by 6 sulfur atoms. This arrangement results in a dense metallic-looking crystal. Now, onto silicates. Silicates are compounds that contain silicon and oxygen, often with other elements as well. Quartz, for example, is a common silicate you might find in a variety of everyday objects, from watches to glass. The crystal structure of quartz is a continuous framework of SiO4 silicon-oxygen tetrahedra, with each oxygen being shared between 2 tetrahedra. This gives quartz its hard and durable properties. So what does all this mean? Well, the bonding and crystal structures of these substances greatly influence their properties. In the case of iron oxide, the cubic structure and bonds between iron and oxygen atoms make it susceptible to corrosion, hence the formation of rust. For iron sulfide, its crystal structure gives it a metallic luster, even though it's not a metal. And as for quartz, its continuous framework of silicon-oxygen tetrahedra makes it one of the hardest common minerals. These are just a few examples, but the principles apply across the board. Whether it's the hardness of a diamond, the conductivity of copper, or the brittleness of glass, the properties of these substances can be traced back to their bonding and crystal structures. So when you look at the world around you, remember that there's a lot happening on a microscopic level. The materials we use, the technology we rely on, even the ground beneath our feet. It's all influenced by the complex interplay of atoms and the structures they form. In essence, understanding the bonding and crystal structures of materials isn't just about knowing what things are made of. It's about understanding why they behave the way they do. It's about seeing the extraordinary in the ordinary. It's about uncovering the hidden world of atoms and molecules that shapes our everyday lives. Understanding the bonding and crystal structures of these substances is key to understanding their properties and behavior. We've covered a lot of ground today, so let's take a moment to recap. We started off by shedding light on chemical bonding, an essential process that allows atoms to connect, forming substances with unique properties. Then we delved into the fascinating realm of crystal structures, revealing how atoms arrange themselves in a patterned, three-dimensional lattice. Our exploration didn't end there. We ventured into the bonding and crystal structures of common oxides, sulphides, and silicates. We discovered how these compounds, each with their distinct chemical bonds and crystal formations, contribute to the diverse world of chemistry. From the oxygen we breathe, represented as oxides, to the sulphides and silicates that make up the Earth's crust, we've seen how understanding these structures helps us comprehend the world around us. Remember, understanding bonding and crystal structures is a crucial step to understanding the world at the molecular level. Keep exploring! Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon and stay curious for new uploads.